Okay, so today we will talk about our midterm, and I will go over this midterm questions with you and tell you what the answer is, and like to ask questions. Okay, if you have this in your hand or not, you all have computers, or so do you need this? Okay, nice. So yeah, it's okay. I can pour it out. Okay, so I think this midterm is a good exercise for you to do. So just try to figure out how should you solve each question instead of focusing too much on the grade. Okay, so that's what I hope. Alright, let's start looking at this exercise 1. So consider the following sets A, B, and C, and then we have a whole bunch of calculation to the set. Okay, so first is the intersection of A and C. So A is A, B, C, D. C is B and C. So the intersections, the only thing in common for them are B and C, right? So intersection of A and C is BC, lowercase bc, 2 elements, right? Let me see if I can write it down. Exercise 1. Okay, and then the intersection of A and B. First we calculate the intersection of A and B, then we calculate its union with C, right? So this is simple, also simple. So A and A intersection B. So the only thing for A and B in common is the element A, right? So it's we need to calculate A, the union of smaller a and lowercase a and the set BCX. So it's gonna be ABCX. Okay, and then it's a difference. It's a difference A and the BX, those two sets. So it's like we remove the common thing from. We remove the second set from A. Okay, so that minus or a slash, they are the same. The difference. Okay. So it's gonna be A minus BX. So the only thing in A is the B because X is not in A at all. So come on. So A minus BX is gonna be where I say, yeah, so ACD. So one thing you need to, it might be a bit confusing is X is an element that is only in the second set but not in the first set, right? So this x over here, this x, right? So you don't need to worry about that at all. Because that thing is, whatever those two sets they have in common, remove them from A. Okay. So this is what will be more clear. The minus of sets. See, this is clear. So it's gonna be remove one thing, remove this, remove that white part from the red. So because nothing of this area to the left side belongs to the red at all, so it just remove those things in common. They have in common. If they don't have anything in common, nothing to remove, right? Okay, so that's A, C, D, and then the last one is the union of A and the element x, lowercase x. Not the union, the intersection. Then we calculate the union of this result with the sets that contains one element y. And we calculate the intersection with C. Right? So the result here, let's see. Let's first look at the thing inside this inner brackets. So A intersection x. Actually, x is not in A at all. So this is going to be empty set, right? So this is the empty set. Empty set, the union of an empty set and this y is gonna be just the y, right? So for this part, this highlighted part, the result is y. Okay, no problem, right? And we calculate the intersection of y and the set C, because y is not in the set C at all. So the final result is, what's final result here? You have taken this, you've already taken this midterm, right? Submit it. Just tell me the answer.
No, sir.
Should be BC.
Should be what?
BC.
BC. Okay, let's make it more clear. Now this is y, right? The first set is y. The second set is C. So it's B, C, X, right? So it's the intersection of y and BCX.
No, sir.
Yeah. They don't have anything in common, right? One has the y, one has the BCX. So it's going to be the empty set or null set, whatever you want to call it. Yeah. Okay. So that's exercise 1, some basic set theory. Alright, exercise 2 is also the set theory. First we have this A, B, and C, which is described but not enumerated. So we are asking you to here, the first thing is compute the set of the intersection of A and B. Let's see, what is A? A is the natural number from 1 to 10. B is the natural number from 0 to 2, which is the x is zero number, but x is greater or equal to 0 and less or equal to 2. So basically, A is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. B is, what is in B?
0, 1, 2.
0, 1, 2. Okay. If we say, if we assume that 0 is not a natural number, it's going to be 1, 2. Okay. Yeah, 1, 2. So, and C is a natural number greater than 2. It's going to be 3, 4, 5, 6, 7, blah, 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 infinity.
In the first class, you asked us to assume 0 as a natural number.
Yeah, yeah, this different assumption there, because I saw two theories.
Yeah, we know that 0, from 0 it's a whole number, and from 1 the natural numbers begin, but you asked us to assume that 0 is a natural number.
Yeah, so let's assume 0 is a natural number, because that's what I saw from, I think, from this book when I see the set theory. Yeah, let's just assume it's 0 is a natural number, because that's when I prepare it for that lecture. There's some assumption here in this book, but actually, yeah, I do heard these two theories, so it's hard to say. But let's assume it's okay. Either way, it will be correct. Okay. For now, let's assume 0 is not. Okay. So the intersection of A and B is gonna be. Anyway, 0 is not in A at all. So the only thing in B is 0, 1, 2. Or 1, 2, whatever. 0, 1, 2, or 1, 2, whatever. And but 0 is not in A. Only 1 and 2 is in A. So the union of A and B is 1, 2. It's 1, 2. Okay. And the not union, the intersection. Okay, then the union of 1C is basically it's gonna be huge, because it's gonna be from 3 to infinite, right? Because that's basically C. That's basically what C is, and it's a union, which means you combine the elements in both sets. All right, so it's gonna be C. All right, so whatever C is, and then the C minus B, it's gonna be, because C and B have nothing in common, so it's still C. Okay. Alright, exercise 3. What's that theory? Exercise 3. Exercise 3. Which one of the following is or is not the propositional logic? Okay, so basically it's easy, right? So which one? Only one of them is
Four is
known.
invalid.
Right, yeah, the fourth is invalid. But 1, 2, 3, they are all propositional logic. But why? Why not? Why 4 is not?
Because there's a conjunction in there and only one thing.
Yeah.
It's P and
So
nothing.
you need to be able to explain it, just like what he did. So, correct. When we have a conjunction there, it has to have two operands. The conjunction is the operator. The operator has to have two operands, one at the left side, one at the right side. The only operator that does not require two operands is the negation operator, right? That's why we have those negation. The first thing we have negation. That's fine because it only required one operand. But in terms of conjunction, it requires two operands. Yeah. 4. The conjunction. Okay, exercise 4. Okay. Formalize in propositional logic the following sentences. Can anyone tell me the answer? Okay, let's look at them one by one. If it rains while the sun shines, a rainbow will appear. This is simple. I won't say too much about it. First, if something, then something. It's gonna be just implication. So it's gonna be rain and sunshine implies what? Rainbow. Then second one, Charles. Yes.
Why would A union C only be C? Wouldn't it be 1, 2, 3, 4, 5, 6, 7, 8, 9?
Why union C?
A and C.
Oh yeah. Sorry, that's a mistake. Thank you for catch that. Yeah, it's gonna be yeah, I saw this the intersection of A and C. So A union C is gonna be everything in A and everything in C. So it's gonna be from 1 to infinite. Infinity. Yep. Okay. Great, thank you. Rain and sunshine. Let's go back here. Propositional stuff. Charles comes if Elsa does, and the other way around. It's a little bit tricky now. So we know Charles and if Charles come if Elsa does. So the Elsa will implies this Charles. And then the other way around. What is the other way around?
I mean equality.
Yeah. So we just need to do this equivalent. Basically, it's Charles, Elsa implies Charles, Charles implies Elsa, right? So it's equality. And we can also say this, change this sentence to Charles come if and only if Elsa does. Yeah. If and only Elsa does. Number 3. John comes just when Peter stays at home. Just when. Just when. Can we say that's the only? Do you feel that just when here? John comes just when Peter stays at home. Is that equality or not?
No.
Implies? So which one implies which?
Not Peter implies John.
Peter implies John?
Not Peter implies John.
Not Peter implies John. Let's see.
Peter home implies Johann comes.
Peter home, John comes, right? Peter home implies John comes. But why not the other way around?
Because the statement as written doesn't say anything about whether or not Peter actively avoids showing up if Johann does.
Says
Or doesn't.
Just when Peter stays at home. So Peter stays home and John.
I guess.
Yeah, so correct. That's not actually a only if thing. So Peter comes just when John comes just when Peter stays at home. No, I actually think this is the only logic there. Because only when Peter stays at home, John will come. Right? Do you think so?
Yeah, I guess.
Yeah. See, John comes just when Peter stays at home, which means no matter who else come, John won't do this, won't trigger John anything. Just Peter will trigger John something, right? So that's the only. Yeah, let me see what I write down here. Yeah, I write down this as a equality. So, yeah. Peter home. Okay. Number 4. We are going unless it is raining. We are going unless it is raining. What does that mean?
We go and not rain.
We go and not rain. We go and not rain. Actually, there's the implication there inside. It's not an and.
Not going implies raining.
Not going implies raining. Yes, that's not going implies raining. Let me see. It's actually from here. It says unless it is raining.
Yes.
We are going unless it is raining, which means
Yes,
if
sir.
it is
Not
raining, we're not going, right? If it's So what we can see here is
If we are not going, then it is raining.
the first thing we can see is if it's raining, implies not going, right? No. Unless it is raining. So not raining implies going, right? Or something like not going implies raining. Yeah. Or we can say not going implies raining. Yeah, they are actually the same thing, right? Yes.
The last one, what if you switch when you're not going? Are they still the same?
Number 4.
Yeah. For negation, not going, and try again. If you switch them around, it's still the same. If you put reading in front of the not going there, but not going there.
Yeah, they are the same. Yeah, the two they are the same. Yeah, they are the same thing. They are the same logic. Yeah. It's just that this statement here, it cannot just directly get something without this negation. So because it's using unless, so logic is here, which means from this unless it's raining means going means not raining. Not raining means going. Not going means raining. So they're the same. Yeah.
What if you get not going and raining? Is that
Not going and raining.
Not going and raining will imply going implies raining.
Yeah, not going and raining.
Is the formula for implication? If it will imply going implies raining.
Which rule is that?
Implication.
Implication where implies it's going or raining. That's the imply. IMPL, right?
Now, according to her, I mean, she wrote not going and on a wrote and.
yeah.
Yeah, that's and. So we cannot say and. Yeah, we shouldn't say and here.
Why not?
Let's see. Not going and raining. Because if you say not going and raining, that's a logic that tells you that we know that we are not going. First, there's the truth, not going. Then there's the truth, raining. Yes, they happen at the same time according to here. However, here we're just saying if we're not going means not raining. Let's think about if we're talking about something tomorrow. Actually, nothing happens yet. You cannot just say not going and raining is already the truth. Okay. So the thing that is already the truth is this implication. This implication is the truth. If we're think about if we're talking about something tomorrow, okay. If it's not raining tomorrow, we will go. If it's not raining tomorrow, we will go to school. So this sentence can be established because it is doing some assumption for tomorrow, right? We can see that today. We can see it's the truth for today. If it's not raining, we're going to school tomorrow. That's the truth for today. But we do not really know whether it is raining or not tomorrow. Okay? So it's not a truth. So the truth, maybe tomorrow it's raining, maybe tomorrow it's not raining, right? So if you're saying not raining and going, and you can also say not going and raining, they are conflict to each other, right? Here, these two expressions, they are the same. There's no contradiction for those two expressions, right? Agree? Right? However, if you are say something like, yeah, that's a good question. Not raining and going, right? We can say not raining and going. We can also say not raining and going, and not going and raining. Those two directly conflict each other. Do you think so?
Yeah.
Right? So let's think. For this to be true, you have to be not raining. Going is true. Raining is false for this expression, right? Going is true, raining is false. For this expression to stand, going has to be false. Raining has to be true. So they directly contradict to each other, and then here, let's look at only one of them. Raining and going. This actually equals to not raining, comma, going. However, this sentence didn't tell us it is raining or not, right? We can only say if raining, blah 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 blah. We can plan for tomorrow. We can plan for tomorrow. The plan is the truth that given by this sentence. The sentence only gives you a plan. It's not telling you whether it is rain or not. But if you're writing like this, raining and going, which means it is already raining or you already going. Okay, clear? Yeah. So that's something tricky here. Yeah. I understand why you're saying we can say not raining and going, because they can establish at the same time. They can be true at the same time. But yeah, like I said, that's not happened yet. For this thing, we are going unless it is raining. It's something that's not happening. We're just we're just doing the plan. The plan is the truth, but nothing happens yet. So we can only describe the plan. Number 5. Charles and Elsa, a brother and sister, or nephew and niece. This is interesting. So this is Charles and Elsa. Charles and Elsa, which implies the brother or sisters. No, the brother and sisters. Or this nephew and niece. Brother, sister, nephew, and niece. But here, shall we put disjunction or exclusive disjunction? It's which one is it? This one or exclusive? Which one? Exclusive? Why do you think it's exclusive?
Because they can be one nephew or niece, but they can't be both.
But why can't they be
Or-
both? I mean, the sentence here doesn't tells anything that it cannot be both, right?
I mean, I didn't put it in exclusive order, but I feel like it makes sense to put it in there. I can understand why you would, but it doesn't say you can't be both.
Yeah. Let's see. Let's go back to this thing, this sentence. Can they be both brother and sister and nephew and niece? Right? They can. Right? So they can be if it's my son and daughter, they're brother and sisters. They're brother and sisters, brother and sister. And if I have a brother, they are the nephew and the niece for that guy, right? So I don't see problem for them to be both. Yeah. I don't see problem to just use the disjunction, right? And this for this sentence it just say or, it doesn't say but not both. Right. And from the meaning of that sentence, I don't say they cannot be both. So yeah. Yeah. So if I say something like the lights can be on or off, it's possible that we put it make more sense we put a exclusive disjunction there, right? Because it doesn't there's nothing trigger them to be both on and off. But here, yeah, it's possible. So I would put this just the or, not exclusive.
Not really necessarily in parentheses.
Huh? Yeah, we do not need the parentheses, but if you have that, it's okay. Yeah, because this is or, and it's a lower priority. So either way, you can leave it there or not. Okay, the last thing is kind of confusing. If I have lost, I can't make a move, then I have lost.
I lost equals cannot move.
Lost.
Or you could put lost equals not move.
So here, this is the thing. If I have lost, I cannot make a move, then I have lost. So this then we do not know what is this then for. So we have to, if it's a programming, we have then there. The computer compiler will tell you there's an error because we do not have if, right? Or if we have else or something there, we do not have a if. So that's an error. But that's something about the natural language. Sometimes there's ambiguity there. So yeah, if this, then is follow this if, because we do not say another if, right? There's only one then here and one if here. So what I will say is I have lost and I cannot make a move implies I have lost. Right? Any other opinion?
That they just imply each other.
Yeah, it looks like they just imply each other. But what you mean is if I have lost implies I cannot make a move and I've lost. Is that what you said?
I'm saying it goes both ways. It's the same as like the second statement, it says Charlie comes if Elsa does, and the other way around.
Yeah.
I mean, it's semantically different,
Oh.
but it's
So you're saying
Same
if
one.
I've lost, I can not make a move. Then I have lost. Oh, you're saying they imply each other?
In case of a draw, can we make a move? In chess, by the way.
I cannot make. Well, I'm lost. Yeah, that actually makes sense. Yeah, I don't know. I don't know the standard answer for this. I don't know the standard answer for this, but I think what you said makes sense. So for this, I would set the answer to be both lost. That's the answer one. Lost. Can't move. Implies lost, which doesn't make sense, but according to that, it looks like this. The second is lost. What did you just say?
In chess, if you cannot make a move, if the game is drawn, can you make a move?
If the game?
Is a draw. I mean, no one loses, no one wins.
Oh, if the game is a draw, can you make a move? If it is true. No. If we go this way, no. No. However, here, yeah. Okay. Looks. This make more sense now. So to answer your question, this can answer your question. This answer can answer your question. So it's a lost, cannot move. They imply each other, equality. So if it's a draw, no move. Okay. If it's something else, no move. But if we choose go this way, we don't know. Yeah. We don't know if it's a draw. What we're gonna do. Yeah. So yeah. So this actually make more sense. Lost and cannot move imply each other. But if you write this like that, like this.
If you cannot make a move, that doesn't necessarily imply that you lost. If the game is a draw, then you cannot make a move as well.
Yeah, that's the typical definition of a draw, is neither side can make a move.
Yeah. Okay, so what he said is, to understand this sentence, is if I have lost, I cannot make a move. If I cannot make a move, then I have lost. So that's what his understanding to this sentence. It depends on your understanding to this sentence, theoretically. Yeah. Because this sentence is already confusing, so there are different possibilities there. Yeah. So that's why it says ambiguity. When we're translating some natural language to propositional logic, maybe based on how well the documentation is written, maybe we can avoid those ambiguity, or it result in some different kinds of expression there. Alright, exercise 5. Okay, here I'm trying to ask you, is this expression a tautology? And I tell you that if that is tautology, you have to check if it's true for all the possible combination of values. So to solve this question, what it meant is, I actually want you to find something that to to try each value to see if it is a tautology. So there are also, we can do some maybe simplification, but I don't see it's more efficient, because if we try it for the first possible value, which is true, 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 it's gonna be against it. Let's see. So we actually here we have a R and R, P, and Q. So for R, P, and Q, if each of them has two possibility, true or false, right? For all of them, how many combinations are there?
9 combinations.
How many?
9.
9? Why do you think it's 9?
There's 3 to the third, or 3 to the squared, so 9. Probably minus 1, so 8.
It's actually 2 to the 3. So it's 2 to the 3. So it's 8. 2 to the 3. 2 times 2 times 2. Right? Because R has 2 possibility, P has 2 possibility, Q has 2 possibility, 2, 2, 2. It's 8. So to quickly write down, what we can do is, because R has this two possible value, true or false, right? So what we can do is, for true and then for false. True, 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 false, false, false. Okay, and then RPQ. P will have so here another trick is, here we can just write down. So here is 4 true and 4 false. Here we just write down 2 true, 2 false, 2 true, 2 false. So it's T, 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 F, F, T, T, F, F. And then for Q, we just write down TF, TF. T, F, T, F, T, F. So that's our possible combination. There are 8 of them. First, we know there are 8 of them, and then we start from the first. First is we change every 4 of them. Then we change every 2 of them, TTFF. Then we change every time, TFTF. Okay. Change every 4 times, change every 2 times, change every time. Okay, so we have those combinations here. What we want to try is if it is true for all possible combinations, which you can see here. So if it's all true, we can actually solve the problem now. First, let's try. If it's all true, we can see negation R is false, right? So it's false, and blah 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 implies blah blah blah. Okay, so it's a false, and something implies something. We already solved that problem because it's a false. False and anything, it will be false. So this whole thing will be false. And false equality to anything according to that truth table on the book, that's the thing that is false. So this whole thing becomes false. Okay. As long as we can find one false here, it's not a tautology. So we can say it's not tautology. As long as you can find one possible combination. Yeah. Okay. Let's remove this. Exercise 6. Okay, so one is negation A. Negation A implies B and C. Two is negation B. Okay, so what did you do to prove A? What have you done to prove A?
Used the first principle and I used the implication rule to transform it to not A,
Okay.
not A or
I'll follow you. Not A. It becomes A, right? A or
yeah, and then the second and then below that I did the negation on the A. So I mean that's just an expedient way of doing that.
okay. So it's A or B and C, and then what else? What did you do next?
And then after that I did the contradiction, and then the second statement 2, and then I referred back to the second one where I negated it, and so what I ended up getting was A or false and C. So I looked at the second statement because it says not B, so that means that B and C is false and C, right?
Let me see. To prove A, so it's gonna be negation B. Let's see. So the second one is negation B.
Right, yeah, then so I referenced that. So not B and C means false and C.
Not B and C. Yeah. So yeah, not B and C means false and C. Yes. Then
And
we
I used
can
the commutative law.
have this A. Yeah. So here, this step, if you remember what I sent an email yesterday, I asked you to not assume like open is true, close is false, things like that. Do not assume value. But here it's different. This negation B just means B is false. Right? Because for this to be true, the B can only be false. Negation B. If B is true, negation B is false, then the second thing won't stand. The second fact is not there. It's not a premise. Yeah. So negation B, which means B is actually B is true, so B is false. So it becomes false, and C.
Yeah,
Right.
and then A is true from before.
Then false and C is actually a false. False and anything will become false.
Yes.
Yeah, so that's the same. Your way is the same.
Yeah, so I was saying above, like A is true because the two negation.
Yeah. So if we're using the MPL, it's gonna be A or
false, and then that means A
false.
is true.
Yeah. A or false. That means A is true. Yeah. A or false, which stands as A. So anything or false can be deduced to that thing, right? That's a rule. That's a or. Which rule is that? I don't have that. All three? Yeah. So this is actually all three from this step to here. Or three. Okay. So exercise 6. That's actually a simple one. Exercise 7. Prove the following theorem. Okay. First, Jim is architect or a travel agent. So HP1. Jim is an architect or travel agent. Okay. HP2. If James is an architect, then James is graduated. So architect implies graduated. And HP3. James is not graduated. Not graduated. So we saw James, this name, in all these three hypotheses. However, we are not using James here because it's not. You can just omit this James thing here because it's all about talking about James is an architect. James is. Not James. The thing James is, they are the same, so they kind of eliminate each other. Okay. So we do not need to mention them in this propositional expression. Then what we want to prove is James is a travel agent. What do we want to prove? Is TA, travel agent. Okay, so we're not saying I think, yeah, you can use a proof, indirect proof, or just proof, either way. Since we want more practice on the indirect proof, let's do this. Now let's assume if we want to do the indirect proof, what do we do? First step, let's assume we want to prove TA, travel agent, right? That's what we want to prove, right? So if we are using indirect proof, what do we do first? Come on.
Prove that it's not true.
Yeah, we assume it's not true. We assume the conclusion is not true. Okay. Then we have all those things. Come on. I just did this. Okay, so TA is not true. We have all those A or TA. Then from TA is not true. TA is false based on this OR 3. OR 3, right?
Yes.
It's gonna be A is A or false becomes A, right? Okay. Nice. Okay. Right now we're from A. We know A is based on 1, 4, and or 3. No A. Then number 6. We know A, then it's based on 5 and 2. We know grade. We know it's graduated. Jamie's graduated. It's based on 2 and 5, right? Because 2 says A implies graduated, and 5 says A. So based on 5 and 2, Jamie is graduated, right? So, and here, number 3, it's already tell us graduated is false. So here is actually a false, which is a conflict. Okay. Confliction there. So we prove that James is a travel agent. So that's the indirect proof. If we are doing direct proof, so which means we only have this thing, we're not assuming TA. So here, how do we do the proof?
Jim's not a grad, so since he is not graduated, he is not. I mean, you can use the implication rule to say
Yeah.
that he is not an architect.
Yeah. So here, graduated is false. Here is A implies false. According to 2 and 3. Right. And number 5.
Not a or false.
Yeah, it's not A or false. Or false. It's the MPL. Then apply implication rule, and then anything or a false becomes that thing. Right. Or 3. And then based on this 1, 7.
So then it's false. Or
Yeah. So it's gonna be a false or have an architecture based on number 6 and based on number 1 and number 6. Then again it's the OR 3 rule, because the TA or false becomes TA, travel agent. Again it's OR 3. Then maybe some other, okay, so we prove that Jim is a travel agent, right? So there are maybe some other way to prove this, some other, you apply some other rule or doing some other transformation to the expression, but finally you will reach there, because the logic is the logic. The logic will, maybe you have different ways to reach the destination, but the truth is truth. The logic is Jim is a travel agent. Okay. So, alright. So that's the midterm. If you have any question, please let me know, or anything that is very confusing, let me know, send me email or make an appointment with me. Yeah, I think from next week I will assume you have all those basic understanding to this proof, this transformation, and what is the reason we can doing each step. Okay, like something like this. I'm gonna assume you have this knowledge, and I will continue with the rest of the course with the semester. All right. Thank you very much for today.